Look up at the night sky, and you'll see countless pinpricks of light, each one a star, part of something far grander. But hidden among them, barely visible to the naked eye, are vast, swirling islands of stars, gas, and dust, galaxies. These cosmic giants, some spanning hundreds of thousands of light years, are the building blocks of our universe. Yet here's the mind-blowing part: every single galaxy, from the smallest dwarf to the largest supercluster, began as nothing more than a tiny ripple in the fabric of space and time. How did these majestic structures, some older than Earth itself, come to exist, and what forces shaped them into the breathtaking spirals, ellipticals, and irregular shapes we observe today? Galaxies aren't just static paintings in the sky, they're alive, evolving, and constantly interacting in ways that defy imagination. Take our own Milky Way, for example. Right now, it's on a collision course with the Andromeda galaxy, a slow-motion dance that will reshape both galaxies billions of years from now. But that's just one chapter in an epic saga that spans nearly 14 billion years. From the violent births of the first stars to the mysterious pull of dark matter, the story of galaxies is filled with twists, turns, and cosmic mysteries waiting to be unraveled. In this video, we're diving deep into 30 fascinating facts about galaxy formation and evolution, facts that will change how you see the universe. You'll discover how galaxies grow, how they die, and why some of them defy all the rules. We'll explore supermassive black holes lurking at their hearts, the invisible scaffolding of dark matter holding them together, and the mind-bending idea that galaxies might even be connected by vast cosmic highways. So if you've ever stared up at the stars and wondered how it all came to be, you're in the right place. Let's begin this journey through space and time, where every fact is a piece of the puzzle and the universe is the ultimate storyteller. It might seem impossible, but galaxies, those magnificent swirls of light, are almost entirely empty. Picture standing in the middle of an endless stadium, with just a few grains of sand scattered across the entire field. That's how sparse the matter in a galaxy truly is. Despite containing billions of stars, they're so spread out that collisions between them are vanishingly rare. The distances are staggering. If our sun were the size of a grain of sand, the next nearest star would be over 4 miles away. Yet from Earth, galaxies appear dense and crowded, their light blending into luminous clouds. That's because even a single star's glow can travel unfathomable distances, tricking our eyes into seeing solidity where there's mostly void. This emptiness plays a crucial role in how galaxies evolve. The vast gaps between stars allow entire solar systems to move without disruption, while the thin soup of gas and dust slowly collects under gravity's pull, birthing new stars over eons. Even the glowing arms of spiral galaxies, which seem packed with starlight, are mostly just illusion, like tracing the outline of a city's lights from space, where the glow masks the darkness between. And here's something even more astonishing. The Milky Way's disk, though 100,000 light-years wide, is only about 1,000 light-years thick on average. That makes our galaxy proportionally thinner than a sheet of paper held at arm's length. So next time you gaze up at the band of stars arching across the night sky, remember, you're looking at a cosmic mirage, a delicate web of light woven across an ocean of nothingness. Our galaxy, the Milky Way, isn't just a peaceful island of stars. It's a cosmic predator, slowly consuming its smaller neighbors to fuel its own growth. Right now, it's tearing apart the Sagittarius dwarf galaxy, a tiny companion that's been orbiting us for billions of years. Gravity stretches this dwarf galaxy into long, shimmering streams of stars, wrapping around the Milky Way like celestial ribbons. These stellar trails are all that remain of what was once an independent galaxy, now reduced to debris in our galactic wake. This process isn't unique, it's how most large galaxies grow. Like a spider weaving its web, the Milky Way's immense gravity captures passing galaxies, pulling them apart over eons. The stars from these mergers don't just vanish, they become part of our galaxy's halo, a vast, diffuse cloud of ancient stars surrounding the main disk. Some of the oldest stars in the Milky Way likely came from similar mergers billions of years ago, making our galactic history a patchwork of devoured neighbors. But here's what's truly fascinating: these collisions aren't violent smash-ups. Stars are so far apart that they rarely collide. Instead, galaxies merge like two clouds of smoke, their stars gradually mixing into a new, larger structure. Even as the Sagittarius dwarf dissolves, its stars will continue orbiting the Milky Way's core, leaving behind ghostly trails that astronomers can trace like cosmic breadcrumbs. These mergers do more than just add stars, they reshape entire galaxies. The influx of new material can trigger bursts of star formation, ignite supermassive black holes at galactic centers, and even warp the Milky Way's spiral arms. And in about 4 billion years, our galaxy will experience its most dramatic merger yet when it collides with Andromeda, creating an entirely new galaxy some call Milkomeda. So every time you look at the night sky, remember, you're not just seeing stars, you're witnessing the aftermath of a cosmic feast where galaxies grow by consuming one another in a dance as old as the universe itself. Galactic collisions sound like the ultimate cosmic catastrophe, two massive islands of stars smashing together in a fiery explosion. But the reality is far more subtle and surprisingly common. Across the universe, galaxies collide all the time, drawn together by their immense gravity. In fact, astronomers estimate that 1 in every 10 galaxies we see today is in the process of merging with another. Our own Milky Way has likely absorbed dozens of smaller galaxies over its lifetime, and in about 4 billion years, it will face its most dramatic encounter, yet a slow-motion cosmic tango with the Andromeda Galaxy. What's astonishing about these mergers is how peaceful they truly are. Despite the sheer scale involved, individual stars almost never collide. Think of it like two crowds of people walking through each other in an enormous stadium. Each person represents a star, and the gaps between them are so vast that actual collisions are nearly impossible. The real action happens in the spaces between those stars, where vast clouds of gas and dust crash together, compressing under gravity's relentless pull. This compression ignites furious waves of new star formation, lighting up galaxies with brilliant bursts of stellar birth. The Milky Way and Andromeda's future merger will be no different. As they draw closer over billions of years, their gravitational dance will warp their spiral arms, flinging stars into new orbits like leaves caught in a whirlwind. The gas between stars will collide, triggering a fireworks display of star formation so intense it could outshine the combined light of both galaxies. But those stars themselves, they'll pass right by one another unharmed, as if moving through a ghostly fog. Even more fascinating is what comes after. The two galaxies won't just bounce apart, they'll gradually merge into a single, larger galaxy, likely forming a smooth, elliptical shape rather than a spiral. This new galaxy, sometimes nicknamed Milkomeda, will be a cosmic melting pot, blending the stars, planets, and histories of both. And if any civilizations exist to witness it, they'll see a night sky transformed, with Andromeda's stars mingling with our own in a dazzling new arrangement. So while galaxy collisions might sound violent, they're more like a slow, graceful ballet, one that reshapes the universe on scales we can barely fathom. And far from being rare, they're one of the universe's most fundamental ways of growing, evolving, and creating new cosmic wonders. If you could see the true structure of a galaxy, you wouldn't just see stars and gas, you'd see an invisible force holding it all together. That force is dark matter, the universe's most mysterious ingredient. Though completely invisible to telescopes, dark matter outweighs all the visible stars, planets, and gas in a galaxy by a factor of 5 to 1. Without it, galaxies would spin themselves apart, flinging stars into the void like a carousel spinning too fast for its own good. Imagine a galaxy as a city at night with streetlights representing stars. From a distance, the lights seem to trace the city's shape, but they're only a small part of the story. The real structure comes from the roads, bridges, and foundations unseen but essential. Dark matter acts like that hidden infrastructure, a vast, shapeless scaffold extending far beyond the galaxy's glowing edges. Its gravity grips stars and gas, keeping them in orbit like an invisible hand guiding a cosmic dance. Here's where things get even stranger. Dark matter doesn't just surround galaxies, it molds them. When the universe was young, dark matter's gravity pulled ordinary matter into its clutches, creating dense patches where galaxies could form. Without it, the first stars might never have clustered together, leaving the universe dark and empty. Even today, dark matter's pull shapes how galaxies move. The Milky Way, for example, isn't just orbiting the center of our local galaxy cluster. It's surfing a river of dark matter flowing through the cosmos. Yet despite its overwhelming presence, dark matter remains elusive. It doesn't emit, absorb, or reflect light, leaving astronomers to detect it indirectly through its gravitational fingerprints. When they map the way galaxies bend light or measure how fast stars orbit their centers, the numbers only make sense if dark matter is there, silently anchoring everything. Some theories suggest it's made of undiscovered particles, while others propose revisions to our understanding of gravity itself. One thing is certain: dark matter is the universe's unsung architect. It built the cosmic web that galaxies cling to, and it continues to shape their evolution billions of years later. So the next time you marvel at a spiral galaxy's graceful arms, remember, they're not just held together by the stars you see, but by an invisible presence we're only beginning to understand. Traveling back through cosmic time, we find GNZ 11, a galaxy so ancient it existed when the universe was just 400 million years old. That's like glimpsing a newborn's first breath in a life that's now over 90 years long. Discovered in 2016 by the Hubble Space Telescope, this faint smudge of light holds the record as the most distant and therefore oldest galaxy ever observed. Its light has taken 13.4 billion years to reach us, meaning we're seeing it as it appeared when the cosmos was a mere 3% of its current age. What makes GNZ 11 so remarkable isn't just its age, it's the secrets it reveals about the universe's chaotic infancy. This galaxy shouldn't have existed, at least not by our old models. The early universe was a fog of hydrogen gas, and scientists thought it would take much longer for gravity to pull matter together into something as structured as a galaxy. Yet there it is, glowing defiantly in the darkness, proving the cosmos got its act together faster than anyone expected. Modern telescopes like the James Webb Space Telescope are rewriting the story of these early galaxies. Because light takes time to travel, looking deeper into space means looking further back in time. JWST infrared eyes can pierce through cosmic dust and spot galaxies even older than GNZ 11, some so distant their light is stretched into invisible wavelengths by the expansion of the universe. Each new discovery peels back another layer, showing us how quickly stars ignited and galaxies assembled in the universe's first chapters. But here's the real mind-bender: GNZ 11 might not even exist anymore. In the billions of years since its light began traveling to us, it could have merged with other galaxies, been torn apart by cosmic forces, or exhausted its star-forming gas. We're seeing a ghost, a snapshot frozen in time from an era when the universe was still taking shape. And as telescopes grow more powerful, who knows what other ancient giants we'll find lurking in the darkness, waiting to tell us their stories. Galaxies are the universe's snowflakes. No two look exactly alike, yet they fall into distinct categories that tell the story of their lives. The most iconic are the spirals, like our Milky Way, with their sweeping arms of stars and gas swirling around a bright central bulge. These galactic pinwheels are cosmic powerhouses where dense clouds of gas collapse into new stars, painting their arms blue with the light of youthful stellar nurseries. But spiral galaxies aren't just pretty faces, their shape reveals an active, dynamic life. That rotation keeps their gas stirred up, fueling star formation for billions of years, while their flat disks act like celestial record players, spinning out the story of their evolution. Then there are the ellipticals, the universe's retired giants. These smooth, featureless galaxies resemble giant blobs of light, lacking the spiral's delicate structure. They're packed with older, redder stars, their gas long since used up or stripped away in violent encounters. Think of them as cosmic museums. Their stars are ancient relics, their shapes molded by past collisions. Some ellipticals are among the largest galaxies known, containing trillions of stars, yet they're strangely quiet, their star-forming days behind them. The fact that they dominate the centers of galaxy clusters hints at a turbulent past, like heavyweight champions who have absorbed countless smaller rivals. And then there are the misfits, irregular galaxies. These cosmic doodles have no defined shape, often twisted by gravity or exploding with chaotic star birth. Some were once orderly spirals until a collision warped them. Others are small and fragile, never having had enough mass to settle into a stable form. The Large Magellanic Cloud, a satellite of the Milky Way, falls into this category, a messy, star-forming world that defies the classic molds. What's fascinating is how a galaxy's shape connects to its history. Spirals, with their ongoing star formation, are the universe's middle-aged strivers. Ellipticals are the elders, their stars born in frenzied bursts long ago. And irregulars, they're the rebels, shaped by chance encounters or left forever young, never settling down. Even the colors tell a story: blue for youth, red for old age, a cosmic gradient painted across the sky. But here's the twist: galaxies can change categories. A spiral colliding with another might lose its delicate arms, morphing into an elliptical over eons. Gravity is the ultimate sculptor, and the universe never stops rearranging its artwork. So the next time you see an image of a galaxy, look beyond its beauty. Its shape is a diary written in starlight, telling the story of billions of years of cosmic evolution. At the heart of nearly every galaxy, including our own Milky Way, lurks an invisible monster, a supermassive black hole. These cosmic behemoths weigh millions to billions of times more than our Sun, crammed into a space smaller than our solar system. The Milky Way's own supermassive black hole, Sagittarius, a star, sits 27,000 light-years away, its gravity silently steering the orbits of hundreds of stars whipping around it at unfathomable speeds. Despite their terrifying reputation, these black holes aren't just destroyers, they're architects, shaping the very galaxies they call home. What's astonishing is how intimately linked a galaxy's fate is to its central black hole. Astronomers have found a bizarre correlation: the larger the galaxy, the more massive its black hole tends to be. This suggests an invisible feedback loop spanning billions of years. When a black hole feeds on surrounding gas, it doesn't just swallow matter quietly. It erupts in violent outbursts of energy, heating up surrounding material and blasting it outward with enough force to shut down star formation across entire galaxies. Imagine a cosmic thermostat. Too much gas falling in triggers a blast that clears the kitchen, preventing galactic obesity. But black holes aren't always chaotic. In quieter phases, their gravity organizes stars into dense clusters around them, creating brilliant hubs of light at galactic centers. The stars orbiting Sagittarius, a star, for example, move faster the closer they get, like a celestial carousel spinning wildly near the center. Watching these stars dance has even allowed scientists to test Einstein's theory of relativity in extreme environments where gravity bends space-time like taffy. Yet the biggest mystery remains: which came first? Did black holes form first and pull galaxies into existence around them? Or did galaxies birth their central black holes from collapsing gas clouds in their early years? Current theories suggest they grew together, with black holes acting as seeds around which galaxies assembled. Some supermassive black holes existed shockingly early, less than 700 million years after the Big Bang, leaving astronomers puzzled about how they grew so fast. One thing is clear: without these gravitational titans, galaxies as we know them wouldn't exist. They're the silent conductors of the cosmic orchestra, their influence reaching far beyond their event horizons. So while we might never see a black hole directly, their fingerprints are everywhere in the swirl of spiral arms, the glow of galactic cores, and perhaps even the very shape of the universe itself. Galaxies spin like cosmic carousels, with stars orbiting their centers at dizzying speeds, but there's a catch. According to the laws of physics, the outer edges should move slower than the inner regions, just like planets farther from the Sun orbit more slowly. Yet when astronomers measured the rotation speeds of galaxies, they found something bizarre. Stars on the outskirts were whipping around just as fast as those near the core, defying all expectations. It's as if a playground carousel kept spinning at the same speed no matter how far out you sat, with kids on the edge clinging impossibly tight without being flung off. This mystery, known as the galaxy rotation problem, sent scientists scrambling for answers in the 1970s. The visible matter in galaxies, stars, gas, and dust simply couldn't account for the gravitational grip needed to keep those outer stars from flying away. Imagine trying to hold a spinning rope with a weight at the end. If the rope isn't strong enough, the weight goes flying. In galaxies, the rope should be gravity from visible matter, but it wasn't nearly enough to explain the observed speeds. Enter dark matter, the invisible glue holding galaxies together. Astronomers realized there must be an enormous amount of unseen mass, weighing 5 times more than all visible matter, creating a gravitational scaffold that extends far beyond a galaxy's glowing edges. This hidden mass explains why stars on the outskirts orbit just as fast as those closer in. They're caught in the pull of an immense invisible halo. Without dark matter's extra gravity, galaxies would spin apart, their outer stars flung into the void like sparks from a fireworks wheel. Here's where it gets even stranger. Dark matter doesn't just lurk in galaxies, it shapes the universe's large-scale structure. Filaments of this mysterious substance form a cosmic web, guiding galaxies into clusters and superclusters over billions of years. The rotation curves of galaxies were our first clue to its existence, a silent revolution in how we understand the cosmos. So the next time you see a spiral galaxy's graceful turn, remember, its beautiful spin is a dance orchestrated by the unseen. Not all galaxies blaze with the vibrant energy of newborn stars. Some are celestial graveyards, their star-forming days long over. These dead galaxies, often massive ellipticals, glow with the reddish hue of aging stars, their gas reservoirs exhausted or stripped away billions of years ago. Unlike spirals, where blue pockets of young stars dot the arms, these galaxies are uniformly red, their stellar populations frozen in time like a cosmic snapshot of the distant past. The mystery lies in how they died. One leading theory points to their supermassive black holes as the culprits. When these black holes feed on surrounding gas, they don't just consume quietly, they unleash catastrophic energy outbursts. These violent eruptions heat surrounding gas to millions of degrees, pushing it out of the galaxy or rendering it too hot to collapse into new stars. It's like a wildfire racing through a forest, leaving behind only embers. Astronomers call this process quenching, and it's as if the galaxy's own heart turned off its star-forming engines. But black holes aren't the only killers. In dense galaxy clusters, a brutal phenomenon called ram pressure stripping can strangle star formation. As a galaxy plows through the hot gas between clusters, the sheer force rips away its own gas reserves, the raw material for new stars like leaves torn from a tree in a hurricane. Without fresh gas, the galaxy's stellar nurseries shut down, leaving it to fade slowly into the red. What's eerie is how abruptly this can happen. observations show some galaxies transition from star-forming powerhouses to dead relics in as little as a few 100 million years, a blink in cosmic time. One moment they're vibrant spirals, the next their light reddens, and they join the ranks of the red and dead. Yet even in death, these galaxies tell a story. Their vast collections of ancient stars preserve clues about the universe's early epochs, like fossils locked in celestial amber. And in a way, their demise paves the way for new cosmic dramas. Their expelled gas may one day fuel star birth in other galaxies, turning death into rebirth on a galactic scale. Forget lonely galaxies drifting through empty space. Our universe is structured like a colossal sponge, with galaxies strung along invisible threads in a vast cosmic web. Picture dewdrops clinging to a spider's silk on a misty morning, except here, the silk is made of dark matter, and the dewdrops are entire galaxies, each containing billions of stars. This intricate network stretches across billions of light years, connecting galactic clusters like beads on a string, with enormous voids, empty regions spanning hundreds of millions of light years between them. The real architect of this web isn't gravity alone. It's dark matter, that mysterious, invisible substance making up most of the universe's mass. In the early cosmos, tiny fluctuations in dark matter's distribution acted like seeds. Over billions of years, gravity amplified these wrinkles, pulling matter into dense filaments where galaxies would eventually form. The result, a universe intricately woven into a three-dimensional tapestry, with galaxies clustered along the intersections of these threads, drawn together like moths to cosmic streetlights. What's breathtaking is the scale. If we could step back far enough to see the web in its entirety, it would resemble the branching veins of a leaf or the neural pathways of a brain, patterns repeating across nature from the microscopic to the cosmic. Even more mind-bending, we're inside this web right now. The Milky Way sits in a filament called the Laniakea supercluster, a structure so vast it contains 100,000 galaxies, all streaming toward a gravitational focal point astronomers call the Great Attractor. But the cosmic web isn't static. It's a living, evolving structure. Galaxies move along these filaments like commuters on a highway, funneled toward dense clusters where they'll eventually merge. The largest knots in the web, like the Virgo cluster, are galactic metropolises packed with thousands of galaxies orbiting a common center. Meanwhile, the voids between filaments are eerily empty, some so devoid of matter they've been called cosmic deserts, where a single galaxy might shine like a lone campfire in an endless night. This web's existence explains why galaxies aren't scattered randomly, but instead form walls, sheets, and clusters. It's the scaffolding of the universe, the hidden blueprint behind everything we see. And with telescopes now mapping these filaments in greater detail, we're uncovering how galaxies are born, move, and collide within this grand design, threads in a tapestry woven by dark matter's invisible hand. When we picture galaxies, majestic spirals like Andromeda or colossal ellipticals like M87 often come to mind, but the universe has a secret: most galaxies are tiny. Dwarf galaxies, some no larger than 1,000th the mass of the Milky Way, outnumber their grand counterparts by hundreds to one. These cosmic minnows are the silent majority, flitting through the cosmos like fireflies in the night. And while they may lack the grandeur of their larger cousins, they hold keys to some of astronomy's deepest mysteries. Take the large and small Magellanic Clouds, our Milky Way's most famous satellite galaxies. These irregular dwarfs orbit our galaxy like moths circling a flame, their shapes distorted by our gravitational pull, but their importance far outweighs their size. Because they're relatively close, just 160,000 light-years away, they serve as laboratories for studying how galaxies form and evolve. Their simpler structures and slower evolution give scientists a clearer view of processes that might be obscured in more complex galaxies. What's fascinating is how these dwarfs test our theories of cosmology. According to leading models, the universe should be teeming with far more dwarf galaxies than we've observed. This missing satellites problem has puzzled astronomers for decades. Some suggest our telescopes simply aren't sensitive enough to detect the faintest ones, while others propose that dark matter behaves differently on small scales, preventing certain dwarfs from forming. Each new discovery, like ultra-faint dwarfs found lurking in the Milky Way's outer halo, brings us closer to solving the puzzle. Yet dwarfs aren't just scientific tools, they're survivors. Many bear scars from encounters with larger galaxies, stretched into tidal streams or stripped of their gas. Some, like the recently discovered feeble giant Crater 2, are so diffuse they're nearly invisible, ghostly remnants of ancient mergers. Others, like the star-forming frenzy in the dwarf galaxy Zwicky 18, defy expectations by birthing new stars long after their peers have gone quiet. These galaxies may be small, but their stories are colossal. They teach us about the universe's earliest days, the nature of dark matter, and even the fate awaiting our own Milky Way as it consumes its satellite family. So next time you gaze at the night sky, remember, for every brilliant spiral you see, there are hundreds of unseen dwarfs whispering secrets about the cosmos' hidden architecture. Galaxies aren't just passive collections of stars they breathe, not in the way we do, but through titanic gusts of gas called galactic winds, blasting outward at millions of miles per hour. These cosmic hurricanes are sculpted by the most violent events in the universe, supernova explosions and the furious energy erupting from supermassive black holes. Picture a fountain on an unimaginable scale, not of water but of star-forming gas, ejected high above a galaxy's disk before raining back down in a celestial cycle of creation and destruction. When a massive star dies in a supernova, it doesn't just vanish. It detonates with the energy of billions of atomic bombs, hurling its outer layers into space at incredible speeds. Multiply this by thousands of exploding stars, and you get a collective force powerful enough to push gas out of the galaxy entirely. It's like a forest fire raging through a dry woodland, but instead of trees, it's the raw material for future stars being swept away. These winds carry heavy elements forged in stellar cores: carbon, oxygen, iron, scattering them across intergalactic space like cosmic seeds. Without this process, the universe would lack the building blocks for planets or even life itself. But supernovae aren't the only force behind these winds. At the heart of many galaxies, supermassive black holes add their own fury. When these monsters feed on surrounding gas, they don't just swallow it quietly. They belch out enormous jets and radiation, heating the gas around them until it erupts outward in a blazing tempest. Some of these outflows are so powerful they can strip entire galaxies of their star-forming fuel, effectively putting them into retirement. Imagine blowing on a dandelion, except instead of seeds, you're scattering enough gas to form millions of stars. What's fascinating is how these winds act like a galactic thermostat. When a galaxy forms stars too quickly, supernova and black hole activity ramp up, ejecting gas and slowing star birth. As things calm down, some of that gas cools and falls back, restarting the cycle. This self-regulation explains why some galaxies aren't as star-rich as they could be. Their own violent outbursts put a brake on their growth. Astronomers have even caught these winds in action. In galaxies like Messier 82, fiery plumes of gas shoot outward like geysers, visible across thousands of light years. These outflows glow with the light of ionized elements, painting vivid streaks across telescope images. And sometimes that ejected gas doesn't escape entirely. It lingers in a galaxy's halo, cooling over millions of years before trickling back down like rain, ready to fuel a new generation of stars. So while galactic winds might sound destructive, they're also creative forces, shaping how galaxies evolve over billions of years. They spread the elements of life, regulate star formation, and even connect galaxies to the vast intergalactic medium around them. In a way, every galaxy is caught in a delicate dance between the winds that scatter its material and the gravity that pulls it back home. Our Milky Way isn't just a flat disk of stars, it's wrapped in an invisible, superheated shroud. This vast spherical halo of gas burns at 1,000,000 degrees, stretching hundreds of thousands of light years in every direction, a ghostly atmosphere surrounding our galactic home. If you could see it with the naked eye, it would appear like a faint, glowing fog, pulsing with the energy of countless atomic collisions. But this isn't just cosmic decoration. It's a dynamic part of our galaxy's life cycle, acting as both a reservoir for future star formation and a shield against intergalactic threats. What makes this halo extraordinary is its origin story. Some of this gas is ancient, leftover from the Milky Way's birth over 13 billion years ago, while the rest is constantly being replenished. Supernova explosions and galactic winds, those violent outflows we discussed earlier, pump hot gas outward where it joins this expansive halo. But here's where it gets fascinating. That gas doesn't just stay there. Over time, it cools and condenses, raining back down onto the galactic disk like a slow mountain waterfall, recycling itself into new generations of stars. In a way, our galaxy breathes, inhaling and exhaling this material over cosmic timescales. This halo also acts as a cosmic buffer, protecting the Milky Way from external dangers. When smaller galaxies or intergalactic gas clouds approach, they slam into this hot barrier first, much like a meteor burning up in Earth's atmosphere. The halo's immense heat and pressure can shred incoming objects, breaking them apart before they reach the delicate star-forming regions below. Without this protective layer, our galaxy might experience far more disruptive collisions, potentially destabilizing the spiral arms we call home. Yet even this giant bubble has its mysteries. Astronomers still debate how much gas the halo truly contains. Some estimates suggest it could hold enough material to build billions of stars, and how exactly it stays so blisteringly hot. Magnetic fields, cosmic rays, and even dark matter might play roles in maintaining its searing temperature, but the full picture remains unclear. Recent observations from space telescopes like Chandra have revealed fingerprints of oxygen, neon, and other heavy elements floating in this halo, clues that help trace its turbulent history. So next time you look at the Milky Way's glowing band arching across the night sky, remember, it's just the visible heart of something far larger. Our entire galaxy is cocooned in this invisible inferno, a silent, swirling ocean of plasma that connects the stars above us to the vast, unexplored reaches beyond. Some galaxies don't fade away gently. They shut down star formation with shocking abruptness, like a factory halting production overnight. Astronomers call this quenching, and it's one of the most dramatic transformations a galaxy can undergo. Picture a bustling metropolis where construction suddenly stops. No new buildings rise, the streets grow quiet, and the skyline remains frozen in time. That's what happens when a galaxy quenches. The vibrant blue glow of young stars fades, replaced by the dull red light of aging stellar populations, as if the entire galaxy has entered retirement. The reasons behind this cosmic shutdown are as varied as they are violent. In dense galaxy clusters, quenching often happens through a brutal process called ram pressure stripping. As galaxies hurtle through these crowded regions at thousands of miles per second, they plow through scorching hot intergalactic gas. This superheated medium acts like a sandblaster, tearing away a galaxy's cold gas reserves, the very fuel needed to forge new stars. It's like driving through a hurricane with your car windows open. Everything loose gets ripped right out. The stripped gas, now heated to millions of degrees, becomes part of the cluster's own atmosphere, leaving the galaxy barren and unable to replenish its stellar nurseries. But environment isn't the only killer. Some galaxies seem to quench from within, their demise orchestrated by their own supermassive black holes. As these black holes feed, they unleash torrents of energy that heat surrounding gas, preventing it from cooling and collapsing into stars. This feedback loop is nature's way of hitting the off switch. Too much star formation leads to too many supernova, which feeds the black hole, which then stifles further star birth. It's a self-regulating system with brutal efficiency, leaving massive elliptical galaxies full of ancient red stars but devoid of the blue sparkle of youth. The speed of quenching is what really stuns astronomers. Observations show some galaxies transition from star-forming powerhouses to dormant relics in less than 1 billion years, a fleeting moment on cosmic timescales. One of the best-studied examples is the massive galaxy cluster Max-J 1931, where dozens of galaxies show signs of rapid quenching. Their outer regions still blaze with newborn stars, while their cores have already gone quiet, as if the shutdown began at the center and spread outward like a wave. Yet quenching isn't always permanent. In rare cases, a dormant galaxy might get a second chance. If it merges with a gas-rich neighbor or drifts into a region with fresh intergalactic material, star formation can reignite. It's like a dormant seed suddenly finding water. The galaxy bursts back to life, if only temporarily. These rejuvenated galaxies are cosmic phoenixes, rare exceptions to the rule that quenching is a one-way street. What makes quenching so fascinating is its role in shaping the universe's large-scale structure. Without it, galaxy clusters would be overflowing with bright blue spirals, and the cosmos would look radically different. Instead, quenching helps create the diverse tapestry we see today, where some galaxies blaze with star birth while others glow faintly red, their stellar factories long silent. So when we look at a dead galaxy, we're not just seeing the end of a story, we're witnessing a pivotal moment in cosmic evolution, where physics and environment conspire to write a galaxy's fate. Stretching our cosmic vision to its limits, we find HD1, a galaxy so distant its light has traveled for over 13.5 billion years to reach us. This faint smudge of infrared light detected in 2022 might just be the most faraway galaxy ever observed, a fleeting glimpse of the universe when it was barely 300 million years old. If confirmed, HD1 isn't just breaking records, it's smashing our expectations of how quickly galaxies could form after the Big Bang. What makes HD1 extraordinary isn't just its distance, it's the sheer audacity of its existence. The galaxy blazes with the light of stars or possibly even a supermassive black hole, shining improbably bright for such an early epoch. Its extreme redshift, a stretching of light into infrared wavelengths caused by the universe's expansion, places it farther back in time than any galaxy previously known, like a single candle flickering in the dawn of cosmic history. Here's where things get puzzling. HD1 brightness suggests it's either birthing stars at a frenzied rate hundreds per year, compared to the Milky Way's sedate 1 or 2, or harboring one of the first supermassive black holes already grown to enormous size impossibly fast. Both scenarios defy current models of galaxy formation. If it's star formation, HD1 must have condensed gas into stars with near-perfect efficiency, a feat likened to filling a football stadium with sand 1 grain at a time in seconds. If it's a black hole, theorists scramble to explain how it accumulated so much mass so soon after the universe's birth. This galaxy isn't just a curiosity, it's a time capsule preserving clues about the universe's cosmic dawn, when the first stars pierced the primordial darkness. The James Webb Space Telescope, with its infrared eyes, is now scrutinizing HD1 and its peers, probing their chemical fingerprints. Early results suggest these ancient galaxies might contain more mature elements than expected, hinting that star formation began even earlier than we'd thought. Yet HD1's greatest gift might be humility. Every time we push our telescopes further, we find galaxies where none should exist, rewriting the timeline of cosmic evolution. It's a reminder that the universe, even in its infancy, was far more dynamic and inventive than our theories predicted. And somewhere out there, even older galaxies likely wait to be discovered, each one a new chapter in the story of how darkness gave way to light. Most galaxies form stars at a leisurely pace, but some go into overdrive, transforming into cosmic fireworks factories known as starburst galaxies. Take the Cigar Galaxy, officially called Messier 82, where stars ignite 100 times faster than in our Milky Way. This celestial frenzy isn't just impressive, it's borderline explosive, with enough stellar births to light up an entire galaxy in just a few million years. What causes such reckless productivity? The answer often lies in galactic collisions, gravitational encounters so powerful they squeeze gas clouds like cosmic sponges, wringing out new stars in torrents. When galaxies collide, the results are anything but gentle. The sheer gravitational chaos compresses vast reservoirs of gas, forcing molecules closer together until they collapse under their own weight. Picture two storm clouds smashing together suddenly. Rain pours down where there was only mist before. In starburst galaxies, that rain is a deluge of star formation, with nurseries so packed they glow fiercely in telescope images. The Cigar Galaxy's frantic activity, for instance, stems from a close encounter with its neighbor, Messier 81, whose gravitational pull sent shockwaves through its gas clouds, igniting a stellar baby boom visible across 20 million light-years. But collisions aren't the only trigger. Some starbursts are fueled by internal instabilities, like bars of stars funneling gas toward galactic centers, or by the violent winds from supermassive black holes compressing surrounding material. The antennae galaxies, a pair mid-collision, showcase both processes in action. Their long tidal tails, stretched like taffy by gravity, sparkle with newborn star clusters, while their cores blaze with the light of countless young, massive stars. These stellar toddlers burn hot and fast, living short, brilliant lives before exploding as supernova, seeding the galaxy with heavy elements. What makes starbursts truly remarkable is their intensity. In the dwarf galaxy Zwicky 18, star formation erupted so recently that most of its stars are younger than life on Earth. Meanwhile, galaxies like NGC 2113 create stars so rapidly they'd exhaust their gas reserves in a mere 100 million years, a cosmic blink compared to the Milky Way's 10 billion-year supply. This unsustainable pace gives starbursts an almost self-destructive edge, like a wildfire consuming its own fuel. Yet for all their fury, starbursts are fleeting. Eventually, the gas runs out, supernova blast the rest away, and the galaxy settles into quiet middle age. But in their brief, brilliant heyday, these cosmic mavericks reshape their surroundings, lighting up the universe with stellar pyrotechnics that echo for eons. So when we observe a starburst galaxy, we're witnessing a cosmic crescendo, one of the universe's most spectacular performances. The Milky Way might look like a serene, flat disk in illustrations, but in reality, it's more like a vinyl record left too close to a heater, warped and twisted at the edges. Recent observations reveal that our galaxy's outer disk bends upward on one side and downward on the other, creating a subtle but unmistakable S-shape when viewed from the side. This cosmic warping stretches across tens of thousands of light-years, far beyond our solar system's relatively flat neighborhood. What could cause such a colossal distortion? The prime suspects are the Milky Way's smaller satellite galaxies, particularly the Large and Small Magellanic Clouds. These cosmic hitchhikers orbit our galaxy, and their gravitational tug, like invisible hands pressing on the edges of a spinning record, slowly twists the disk over time. Computer simulations show that as these dwarf galaxies pass through the Milky Way's dark matter halo, their gravity ripples through the outer gas and stars, bending the disk into its current shape. But there's another twist to the story. Dark matter might be amplifying the effect. Some theories suggest the Milky Way's invisible halo isn't perfectly spherical. It could be lopsided, adding an extra layer of gravitational imbalance that exaggerates the warp. Imagine trying to balance a wobbly table by stacking books unevenly under one leg. The table tilts even more. Similarly, an asymmetrical dark matter distribution could be pulling our galaxy's disk further out of alignment. The warp isn't static, it moves. Like a slow-motion wave traveling through water, the distortion rotates around the galactic center, completing a full cycle every few 100 million years. Stars and gas along the warped edges experience this motion, bobbing up and down as they orbit, much like a car driving over gentle rolling hills. This discovery reshapes how we see our galactic home. Far from being a perfect spiral, the Milky Way is a dynamic, ever-changing structure, its form sculpted by invisible forces and cosmic neighbors. So next time you picture our galaxy, remember, it's not just a flat pinwheel but a celestial vinyl, quietly warping to the rhythm of the universe's gravity. At the heart of most galaxies, one supermassive black hole rules supreme, but nature loves exceptions. Some galaxies defy the norm by hosting not one, but two of these gravitational titans locked in a slow cosmic dance. These rare double nuclei systems are the smoking guns of past galactic mergers, where two galaxies collided and their central black holes became trapped in a gravitational embrace. Imagine two whirlpools spinning around each other in a vast ocean, each dragging stars and gas along their furious orbits while inching inevitably closer over billions of years. The most famous example lies in the heart of Markarian 739, a galaxy 600 million light-years away where twin black holes whirl just 750 light-years apart, cosmically speaking, close enough to reach out and touch. Their presence betrays a violent history. Two galaxies once merged, their black holes sinking to the shared center as swirling gas and stars smoothed out their differences. Now these leftovers circle each other, warping space-time so intensely they emit telltale flickers of X-rays and radio waves as they feast on surrounding material. But such duos aren't destined to last. As they orbit, they lose energy by flinging stars outward and stirring gravitational waves, ripples in spacetime predicted by Einstein. This slow drain ensures they'll spiral together until, finally, they collide in one of the universe's most catastrophic events. When that happens, the merger unleashes a burst of gravitational waves powerful enough to briefly outshine every star in the observable universe combined. The resulting black hole recoils like a cosmic cannon, sometimes kicked clear out of its host galaxy to wander the void alone. Yet catching this finale in action is nearly impossible. The final plunge takes mere centuries, a blink on galactic timescales, leaving astronomers to piece together clues from oddities like Galaxy OJ287, where a recoiling black hole trails a glowing jet bent like a garden hose spraying wildly off-center. Most double nuclei we spot are still centuries or millennia from their fateful collision, frozen in mid-dance like partners waiting for the music's final note. What's mesmerizing is how these pairs sculpt their galaxies long before merging. Their gravitational tug of war can carve out vast empty regions in stellar orbits, create lopsided jets of radiation, or trigger violent bursts of star formation as they stir the galactic pot. And while single black holes typically anchor their galaxies calmly, a duo turns the core into a chaotic arena where only the most resilient stars survive. So when we find a galaxy with two hearts, we're glimpsing both its past and future, a snapshot of cosmic evolution where gravity writes the rules, and even the mightiest black holes must eventually yield. Buried in the light of every star is a secret, a cosmic fingerprint revealing not just its age and birthplace, but the turbulent history of the galaxy it calls home. Astronomers call this galactic archaeology, and it works much like digging through layers of ancient ruins. By analyzing starlight with powerful spectrographs, scientists can detect trace elements fused in long-dead stellar furnaces, turning entire galaxies into sprawling history books written in the language of chemistry and motion. Take the Milky Way's oldest stars, those ancient metal-poor relics found in its halo and globular clusters. These aging giants formed when the universe was young, composed almost entirely of hydrogen and helium, the only elements available after the Big Bang. Their lack of heavier elements like carbon or iron tells us they were born before later generations of stars had time to seed the cosmos with these materials through supernova explosions. Spotting these primordial stars is like finding cave paintings hidden in a modern city, direct evidence of our galaxy's earliest chapters. But stars don't just record their birth conditions, they also carry clues about their travels. Some stars in the Milky Way's halo move in strange, looping orbits or contain chemical signatures that don't match our galaxy's native populations. These celestial misfits are likely survivors of past galactic mergers, refugees from smaller galaxies torn apart by the Milky Way's gravity billions of years ago. One famous example is Omega Centauri, a massive globular cluster that might be the remnant core of a dwarf galaxy devoured long ago. Its stars have distinct compositions compared to the Milky Way's own, like finding pottery shards from a lost civilization mixed into a modern city's foundations. The same techniques unveil dramatic events. When astronomers studied stars in the Andromeda galaxy, they found evidence of a colossal collision, a galactic crime scene, preserved in stellar motions and compositions. Two distinct populations of stars orbit Andromeda's core in perpendicular planes, suggesting it absorbed a massive companion galaxy nearly 10 billion years ago. The stars from that merger still move differently than Andromeda's native stars, their orbits frozen in celestial amber like witnesses to an ancient catastrophe. Galactic archaeology isn't limited to visible starlight. The Gaia Space Telescope has revolutionized the field by precisely mapping the positions and motions of over 1 billion Milky Way stars. This data reveals faint, stellar streams, ribbons of stars stretched into cosmic taffy by gravitational encounters that trace the orbits of long-digested satellite galaxies. Some streams even wrap around the Milky Way multiple times, like ghostly echoes of past mergers. Perhaps most astonishing is how these stellar fossils can pinpoint exact moments in galactic history. In 2022, astronomers identified a group of stars near the Milky Way's core with such similar ages and compositions that they must have formed together in a single burst of star formation, likely triggered by a dramatic event like a gas cloud collision or a close encounter with another galaxy. It's as if we've found a celestial timestamp marking precisely when our galaxy experienced a growth spurt over 10 billion years ago. This detective work extends beyond individual galaxies. By comparing stellar populations across different galaxies, astronomers reconstruct the universe's chemical evolution, how heavier elements gradually accumulated over cosmic time. Dwarf galaxies, with their slower star formation, often preserve pristine examples of early universe chemistry, while massive ellipticals show the end result of countless stellar generations. Together, they form a cosmic family tree, with stars as the living DNA that connects them. So while telescopes show us galaxies as they appear today, galactic archaeology reveals them as they were violent, ever-changing, and constantly rewriting their own stories. Every star is a time capsule, and with the right tools, we can unpack billions of years of history written in their light. Our galaxy isn't floating alone in the void. It's part of a tight-knit community called the local group, a modest gathering of galaxies spanning about 10 million light-years. Picture a cosmic village where the Milky Way and Andromeda are the two largest houses, with dozens of smaller satellite galaxies orbiting them like loyal pets. This neighborhood might seem insignificant compared to the vast universe, but for us, it's everything, the only corner of space we'll ever directly explore beyond our own galaxy. What makes the local group special is its intimacy. While galaxy clusters elsewhere contain thousands of members, our group has just 3 major galaxies: the Milky Way, Andromeda, and the Triangulum Galaxy, plus over 50 smaller dwarfs. Gravity binds them together in a delicate dance that's lasted billions of years, with Andromeda and the Milky Way slowly closing the distance for their eventual collision. The smaller galaxies, like the Large and Small Magellanic Clouds, weave around these giants, some destined to be absorbed while others may orbit indefinitely. The local group also acts as a protective bubble in an expanding universe. While distant galaxies race away from us due to cosmic expansion, our group remains gravitationally linked, like friends holding hands against a strong wind. This means that even as the universe grows more isolated, we'll always have Andromeda and our other neighbors nearby, a cosmic safety net in an increasingly lonely cosmos. But don't mistake local for small. The entire group still spans unimaginable distances. If the Milky Way were the size of a dinner plate, Andromeda would be another plate about 25 feet away, with the farthest members of our group scattered across a football field. And within that space, countless stars, planets, and possibilities exist, each galaxy its own island of potential life and mystery. What's fascinating is how much we've learned about the universe by studying this tiny sample. The local group contains examples of nearly every galaxy-type: spirals, ellipticals, irregulars, making it a perfect laboratory for understanding cosmic evolution. Because these galaxies are close enough to study in detail, astronomers can track individual stars within them, mapping their motions and compositions like detectives reconstructing a crime scene. The future of the local group holds even more drama. In about 4 billion years, the Milky Way and Andromeda will merge, their stars mixing to form a new elliptical galaxy. The Triangulum Galaxy might join the collision or be flung outward by gravitational forces. Smaller galaxies will be torn apart or absorbed, their stars becoming part of the new hybrid galaxy's halo. It's a reminder that even our galactic neighborhood is constantly evolving, with gravity as the ultimate architect of its destiny. So while the local group might seem like a quiet backwater compared to the universe's sprawling superclusters, it's our backwater, a pocket of cosmic real estate where the Milky Way story intertwines with its closest neighbors. And as we peer deeper into its mysteries, we're not just exploring distant galaxies, we're uncovering the shared history that connects us all. Some stars don't just orbit their galaxies, they escape them entirely, rocketing into intergalactic space at speeds that defy imagination. These runaway stars, known as hypervelocity stars, are cosmic fugitives flung outward by forces so powerful they break free from their home galaxy's gravitational pull forever. Picture a slingshot loaded with a marble, except instead of elastic, it's the tremendous gravity of a supermassive black hole, and the marble is an entire star hurtling through the void at over 1,000,000 miles per hour. The most common ejection mechanism involves a dance too dangerous for most stars to survive. When binary star systems, pairs of stars orbiting each other, wander too close to a galaxy's central black hole, the black hole's gravity can tear them apart. One star gets captured into orbit while the other is catapulted outward at blistering speeds, like a stone skipping off the surface of a pond. The energy transfer is so violent that the ejected star can reach velocities up to 10 times faster than typical galactic motions, enough to escape even the Milky Way's immense grip. Astronomers first discovered these stellar outlaws in 2005, spotting a massive blue star racing away from our galaxy's center at nearly 1.6 million miles per hour. Since then, dozens more have been identified, each telling a unique story. Some are young, hot stars betraying their origins near galactic cores, while others are ancient travelers that have crossed intergalactic space for millions of years. A few may even originate from other galaxies entirely, flung our way during collisions or close encounters. What's astonishing is where these stars end up. Unlike most celestial objects bound to their galaxies, hypervelocity stars traverse the lonely expanses between galaxies, where distances are so vast they may never encounter another star again. Over billions of years, they'll drift through the freezing darkness of intergalactic space, their light fading into near invisibility. Yet their journeys aren't entirely solitary. Some may pass through the sparse gas lingering between galaxies, creating shimmering bow shocks like ships plowing through cosmic seas. The existence of these rogue stars reshapes how we understand galactic dynamics. They prove that galaxies aren't just passive collections of stars but active engines capable of flinging their own material into the void. Some hypervelocity stars might even carry planets with them, worlds ripped from their original neighborhoods and condemned to an eternal voyage through the endless night. So while we often think of galaxies as places where stars live, they are also factories producing celestial nomad stars destined to wander the universe alone. Long before sprawling spirals and massive ellipticals dominated the cosmos, the universe's first galaxies were mere specks, tiny, fragile things no larger than modern-day star clusters. These primordial building blocks, sometimes called proto-galaxies, flickered to life when the universe was just a few 100 million years old, their faint glow piercing the darkness of the cosmic dawn. Picture a sky not filled with majestic spirals, but instead dotted with faint, blobby smudges, each containing perhaps 1 million stars, a far cry from the hundreds of billions in galaxies like our Milky Way. What made these early galaxies so small? The answer lies in the scarcity of raw materials. In the universe's infancy, most matter still existed as diffuse clouds of hydrogen and helium, with only slight density variations left over from the Big Bang. Gravity worked slowly to pull these wispy gas clouds together, and without heavy elements to help cool and condense the gas, star formation was inefficient. The first protogalaxies were like delicate soap bubbles, small, ephemeral, and prone to merging at the slightest gravitational nudge. Yet these modest beginnings laid the foundation for everything that followed. Over billions of years, protogalaxies collided and merged, their combined gravity drawing in more gas and neighbors. Like droplets of water merging into puddles, then streams, then rivers, these early structures grew hierarchically, with each merger adding mass and complexity. Computer simulations show this process vividly: tiny clumps of stars swirling together, their orbits chaotically reorganizing until they settled into larger, more stable structures. Some of these mergers were gentle, while others triggered violent bursts of star formation, lighting up the early universe with brilliant blue flashes. One of the best-studied examples of this growth comes from the ultra-faint dwarf galaxies orbiting the Milky Way. These ancient relics, such as Segway 1 or Boots Eye, contain just a few thousand stars but are thought to be surviving fragments of the universe's first galactic building blocks. Their chemical composition almost entirely hydrogen and helium, with barely a trace of heavier elements, mirrors that of the earliest protogalaxies, offering a living snapshot of the cosmos's toddler years. But the real marvel is how quickly the universe scaled up. Within 1 billion years, some protogalaxies had already assembled into larger structures, forming the seeds of today's majestic spirals and ellipticals. Dark matter played a starring role, its invisible filaments funneling gas and galaxies together into dense knots where mergers happened faster. The most massive modern galaxies, like the supergiant ellipticals at the hearts of clusters, likely grew through relentless cannibalism, absorbing hundreds of smaller neighbors over cosmic time. So when we gaze at a galaxy today, we're seeing the endpoint of a growth spurt that began with the tiniest of seeds, a reminder that even the grandest cosmic structures started as nothing more than faint sparks in the darkness. Galaxies don't evolve in isolation. They're shaped by invisible gravitational hands reaching across the void, stretching and twisting them in a cosmic tug-of-war. These forces, known as galactic tides, act like ocean tides on an unimaginable scale, warping galaxies and triggering bursts of star formation as they interact. Picture two dancers spinning close enough to stretch each other's arms outward, except instead of limbs, its entire spiral arms and gas clouds being pulled into dazzling new shapes. The Milky Way itself is both a sculptor and a canvas for these tidal forces. Our galaxy's most famous satellites, the Large and Small Magellanic Clouds, are caught in its gravitational grip, but the influence goes both ways. As these dwarf galaxies orbit, their gravity tugs at the Milky Way's outer gas and stars, creating subtle ripples and even igniting star formation in unexpected places. One stunning example is the Magellanic Stream, a ribbon of gas torn from these dwarfs that stretches across the sky, evidence of a gravitational struggle lasting billions of years. But tides don't just warp galaxies, they can breathe new life into them. When galaxies swing close together, their mutual gravity compresses vast clouds of gas, squeezing them until they collapse into fiery newborn stars. The Tadpole Galaxy, with its long, star-studded tail, shows this process in action. Its dramatic shape was carved by a close encounter with another galaxy, the tidal forces stretching it like taffy while simultaneously lighting up its tail with brilliant blue clusters of young stars. These tidal dwarf galaxies, forged from the debris of collisions, defy expectations by forming new stellar systems from what should be destruction. Even more fascinating is how tides act as cosmic matchmakers for supermassive black holes. When galaxies merge, tidal forces funnel gas and stars toward their central black holes, feeding them until they erupt in dazzling quasars. Without these gravitational nudges, many black holes might starve in silence, but tides ensure they get a feast, sometimes awakening them from dormancy to become the brightest objects in the universe. Yet tidal forces can also be destructive. Small galaxies venturing too close to larger ones often face annihilation, their stars scattered into ghostly streams, like the Helmy Stream, a remnant of a dwarf galaxy torn apart by the Milky Way long ago. These tidal debris trails, though haunting, are treasure troves for astronomers, revealing the history of galactic encounters written in starlight. So while gravity binds galaxies together, it's the tides between them that shape their stories, stretching, squeezing, and sometimes tearing them apart, all while painting the cosmos with new stars. Whether creating or destroying, these unseen forces remind us that no galaxy is an island, each one is part of a dynamic, ever-changing web of gravitational relationships. Most of the galaxies we see glow with the light of billions of stars, but some aren't visible at all. These ghostly structures, known as dark galaxies, are made almost entirely of dark matter, with only a wisp of ordinary matter to betray their presence. Imagine an entire city at night with just a single street lamp flickering. That's what a dark galaxy looks like on a cosmic scale. Their existence pushes the limits of how we define a galaxy, challenging our assumptions about how these cosmic islands form and evolve. So how do we find something that emits almost no light? The answer lies in gravity's fingerprints. Dark galaxies reveal themselves by bending the light of background objects, an effect called gravitational lensing. When astronomers spot distant galaxies or quasars whose light appears strangely warped, but there's no visible galaxy causing the distortion, they've likely found a dark galaxy's shadowy bulk. Another clue comes from rogue clouds of hydrogen gas drifting through space with no stars to illuminate them. These gas clouds rotate as if held together by unseen mass, orbiting invisible centers of gravity like planets around a star they can't see. One of the best-studied examples is Dragonfly 44, a galaxy in the Coma cluster that emits just 1% of the light expected for its mass. At first glance, it looks like a faint smudge, but measurements of its star's motions revealed something startling. Those stars are whipping around so fast that without an enormous halo of dark matter binding them, the galaxy would fly apart. Dragonfly 44 is 99.99% dark matter, making it nearly invisible in every sense except gravity's pull. Even stranger are the completely starless dark galaxies, vast clumps of dark matter and trace gas that never ignited significant star formation. These cosmic phantoms might be failed galaxies, stunted early in their development when their gas was stripped away or prevented from cooling. Others could be remnants of galactic collisions, dark matter halos left behind when their visible matter was torn away. Simulations suggest there could be far more dark galaxies than luminous ones, lurking unseen throughout the universe like shadowy counterparts to the galaxies we know. The hunt for these invisible giants isn't just academic, it could solve one of dark matter's biggest mysteries. If dark galaxies behave differently than predicted, it might mean dark matter isn't what we think. Some theories suggest dark matter could interact with itself, creating cosmic structures even more bizarre than we've imagined. Every dark galaxy discovered is another piece of the puzzle, another clue to the universe's hidden architecture. So while we marvel at the glittering spirals and ellipticals lighting up telescope images, we should remember the cosmos is far richer than what meets the eye. For every glowing galaxy, there may be countless others hiding in plain sight, their presence felt only by the subtle tug of gravity on the fabric of space itself. The universe has a strange case of missing galaxies, or at least that's what our simulations suggest should exist around the Milky Way. According to the most widely accepted models of cosmic evolution, our galaxy should be surrounded by hundreds, even thousands, of tiny dwarf galaxies, each a faint smudge of stars bound together by dark matter. Yet when astronomers scour the skies, they find only a few dozen of these celestial minnows. This glaring mismatch between theory and observation, known as the missing satellites problem, has puzzled scientists for decades, sparking debates about everything from dark matter's nature to the very foundations of galaxy formation. Here's why the numbers don't add up. Supercomputer simulations of the universe, based on the prevailing cosmological model, show dark matter clumping into countless small halos shortly after the Big Bang. These halos should have attracted gas, forming stars and becoming dwarf galaxies, the building blocks of larger structures like the Milky Way. The math predicts swarms of them like fireflies around a lantern. Yet in reality, our galactic neighborhood feels eerily underpopulated. Even accounting for the difficulty of spotting ultra-faint dwarfs, the gap remains staggering. Where did they all go? One possibility is that many dwarfs never lit up in the first place. Some dark matter halos might have been too small or too late to gather enough gas to form stars, leaving them invisible to telescopes. These dark galaxies, composed almost entirely of dark matter with only trace hydrogen gas, could be hiding in plain sight, detectable only through their gravitational influence. Surveys using radio telescopes have indeed found suspicious clouds of hydrogen with no visible stars, potential candidates for these elusive shadows. Another explanation involves our galaxy's violent history. The Milky Way's gravity is relentless, and over billions of years it may have torn apart countless dwarfs, shredding them into stellar streams that now orbit unseen. The remnants of these ancient mergers, like the Gaia sausage or the Helmy stream, are all that remain of galaxies long consumed. Simulations show smaller dwarfs are especially vulnerable, their fragile structures no match for tidal forces. If true, the missing satellites aren't missing, they're simply dissolved. Their stars assimilated into the Milky Way's halo-like spices stirred into cosmic soup. Yet some astronomers suspect the problem isn't with the dwarfs, it's with our models. Could dark matter behave differently on small scales than we assume? Alternative theories like warm dark matter or self-interacting dark matter propose particles that move faster or collide, smoothing out small-scale clumps and reducing the number of expected dwarfs. Others suggest early radiation from the first stars might have sterilized gas in the smallest halos, preventing star formation. Each tweak to the theory offers new predictions, and with next-generation telescopes like the Vera Rubin Observatory set to discover hundreds more faint dwarfs, we may soon know which explanation holds water. The mystery deepens when we compare the Milky Way to its galactic neighbors. Andromeda, for instance, hosts a richer family of satellites than we do, though still fewer than simulations predict. Meanwhile, isolated dwarf galaxies in the cosmic void, like the lonely KKR-25, challenge the idea that environment alone decides a dwarf's fate. It's as if the universe handed out a rulebook for galaxy formation, but some galaxies ignored the instructions entirely. Whatever the answer, these missing satellites are more than a cosmic accounting error. They're clues to the universe's hidden workings. Solving the puzzle could reshape our understanding of dark matter, galactic evolution, and even the fate of our own Milky Way. So while the dwarfs we see are fascinating, it's the ones we don't that might hold the universe's biggest secrets. Most galaxies spin like dinner plates, their stars and gas swirling in a flat disk, but nature has its rebels. Enter polar ring galaxies, cosmic oddities where a bright ring of stars, gas, and dust orbits at right angles to the main disk, like a hula hoop spinning around a frisbee. These rare galactic hybrids defy expectations, their perpendicular rings suggesting histories written in celestial collisions and gravitational acrobatics. One of the most stunning examples is NGC 4650, a galaxy 250 million light-years away where a luminous ring stretches 60,000 light-years across, tilted sharply against its central disk. This striking feature might look like a flaw in cosmic design, but it's actually a fossil record of galactic violence. The leading theory suggests these rings form when a smaller galaxy, rich in gas, plunges through a larger one edge-on. As the intruder is torn apart by tidal forces, its debris is flung into this perpendicular orbit, trapped by the larger galaxy's gravity. Over time, the scattered gas and stars organize into a crisp ring, forever memorializing the encounter. But collisions aren't the only possible explanation. Some polar rings might form from captured intergalactic gas, siphoned from the cosmic web or stolen during close encounters. As this gas funnels toward the galaxy's poles, compressed by gravitational forces, it ignites star formation, crafting a sparkling belt around the galactic waste. Others could be the result of extreme warping, where a galaxy's disk becomes so distorted by gravitational interactions that it buckles into a ring-like structure. The truth may vary from case to case. Nature rarely follows a single script. What makes these galaxies truly mesmerizing is how they challenge our intuition about cosmic motion. In a polar ring system, stars and gas orbit in two nearly perpendicular planes simultaneously, creating a gravitational ballet that would baffle Newton. The central disk spins one way while the ring whirls around it like a cosmic carousel, their paths intersecting at stark right angles. This chaos isn't permanent, though. Over hundreds of millions of years, friction and gravitational tugs will gradually align the ring with the disk, erasing this celestial oddity. Polar ring galaxies are more than just curiosities. They're natural laboratories for studying dark matter. Because the ring and disk orbit independently, astronomers can map the galaxy's gravitational field in 3 dimensions, revealing how dark matter is distributed. The motions of these structures have already hinted that dark matter halos might be flattened along the polar axis, a clue to its mysterious properties. Yet for all their scientific value, these galaxies also serve as a reminder of the universe's creativity. Even something as fundamental as a galaxy's shape isn't set in stone. It can be twisted, warped, and reinvented by the forces of gravity and time. So while most galaxies follow the rules, a handful dance to their own rhythm, wearing their rings at impossible angles like cosmic fashion rebels. Galaxies might seem like limitless star factories, but they operate under strict cosmic quotas, self-regulating their growth through explosive processes called galactic feedback. This balancing act begins when young, massive stars live fast and die hard, exploding as supernova that blast surrounding gas outward at millions of miles per hour. Imagine a wildfire raging through a forest, only for its own winds to scatter the remaining fuel, snuffing out the flames it once fed. That's the paradox of stellar feedback. The same stars that ignite star formation can also extinguish it. But stars aren't the only enforcers. Supermassive black holes play an even more dramatic role. When these monsters at galactic centers feast on gas, they don't just swallow quietly. They belch out colossal jets of energy and radiation, heating surrounding material to temperatures so extreme it can't cool and collapse into new stars. The galaxy's core becomes a cosmic pressure cooker with shock waves rippling outward like a pebble dropped in a pond, except these waves can span thousands of light years. In extreme cases, like the Phoenix Cluster's central galaxy, these outbursts carve cavities in surrounding gas so vast they could swallow our entire Milky Way. This feedback loop isn't just destruction, it's a finely tuned thermostat. When a galaxy forms stars too quickly, supernova and black hole activity ramp up, ejecting gas and slamming the brakes on further growth. As things settle, some of that expelled gas cools and trickles back, restarting the cycle. The result: galaxies avoid burning through their fuel too fast, stretching their star-forming epochs across billions of years instead of flaming out in a brief, brilliant burst. Take the Sombrero Galaxy, where feedback has created a striking equilibrium. Its central black hole is active but not overt, its star formation steady but not explosive. Meanwhile, galaxies like Messier 87 show what happens when feedback runs unchecked. Its jets have blasted away so much gas that it's now a red and dead elliptical, its star-forming days long over. This self-regulation even explains why the universe isn't drowning in dwarf galaxies. Small galaxies have shallow gravitational wells, making it easy for feedback to blow their gas away entirely, like trying to light a candle in a hurricane. Larger galaxies, with their deeper gravity, can retain enough gas to keep forming stars, but only in moderation. So while feedback might sound like galactic self-sabotage, it's actually the universe's way of maintaining balance, a reminder that even in the cosmos, growth without limits leads to collapse, and destruction can pave the way for renewal. The universe isn't just evolving, it's stretching, carrying galaxies away from each other in a relentless expansion that began with the Big Bang. While our local group remains gravitationally bound, with the Milky Way and Andromeda destined to collide, nearly every other galaxy beyond our immediate neighborhood is racing into the void. The farther away they are, the faster they recede, not because galaxies are moving through space, but because space itself is growing between them like dots on an inflating balloon. This cosmic expansion, discovered by Edwin Hubble in the 1920s, means that over time, the universe outside our local group will grow quieter, emptier, and ultimately unreachable. One of the most startling consequences is the fate awaiting distant galaxies we see today. Take the stunning Whirlpool Galaxy, 40 million light-years away, its light reaching us now left when Earth teemed with prehistoric mammals. Due to cosmic expansion, the whirlpool isn't just drifting, it's being carried away by the stretching fabric of space-time. In tens of billions of years, galaxies like it will vanish from our view entirely, their light stretched into invisibility as the expansion accelerates. Future civilizations, if any arise, might gaze into the night sky and see only darkness beyond the Milky Way's merged descendants, with no evidence that trillions of other galaxies ever existed. This acceleration, driven by the mysterious force we call dark energy, ensures the universe's expansion will only speed up. Current measurements suggest that in about 150 billion years, all galaxies outside the local group will have crossed an invisible horizon, receding faster than light can bridge the gap. The cosmos will fracture into isolated islands, each surrounded by an endless, expanding void. Communication, or even observation between these islands will become impossible, as the space between them grows faster than signals can traverse it. Yet there's a poetic irony to this grand isolation. The same expansion that will eventually render most of the universe invisible is also what allows us to glimpse its history. As we look deeper into space, we peer further back in time, seeing galaxies as they were billions of years ago, their light only now reaching us across the growing cosmic distance. The very expansion that will one day hide most of the cosmos from view also preserves its past like a celestial time capsule etched into the sky. For now, we live in a privileged moment, a cosmic sweet spot where the universe is old enough to host mature galaxies and life, yet young enough that the cosmos remains richly interconnected. But the fate written in the stars is clear. The universe is headed toward a lonely future where galaxies beyond our own will fade like distant ships vanishing into fog. So while we still can, we look capturing the light of galaxies racing away, knowing each photon carries a story from a time when the cosmos was closer, brighter, and full of neighbors. Galaxies aren't always destined to fade quietly into the cosmic night. Some get a second act. While most dead galaxies, their gas exhausted or stripped away, glow faintly with the reddish light of aging stars, a rare few defy expectations by reigniting star formation in spectacular late-life bursts. Imagine a retired athlete suddenly returning to break records, or a dormant volcano roaring back to life. Stellar rebirth on a galactic scale is just as dramatic. These cosmic phoenixes typically owe their revival to a lucky encounter, a collision with a gas-rich dwarf galaxy, or even a plunge through a dense filament of intergalactic gas can deliver the fuel needed to restart star formation. The galaxy UGC 3672, for example, was once a quiet elliptical, its star-forming days long over, until it encountered a massive reservoir of cold gas. By 2018, astronomers spotted blue tendrils of newborn stars swirling through its core, clear evidence of a celestial resurrection in progress. The gas, likely stripped from a passing neighbor, cooled and condensed, giving the galaxy's remaining dust and molecular clouds the raw material for a new generation of stars. But mergers aren't the only path to rebirth. Some galaxies, like NGC 4513, flicker back to life thanks to internal processes. Supermassive black holes, often seen as star formation killers, can sometimes play the opposite role. If an accretion event is mild enough, a gentle trickle of gas rather than a violent feast, the resulting energy output might compress surrounding gas clouds just enough to spark localized star birth without blowing the entire reservoir away. It's like stoking a dying fire with careful pokes rather than dumping gasoline on it. The most extreme cases occur in galaxy clusters, where the intergalactic medium is so hot and dense it can act like a pressure cooker. As red and dead galaxies orbit through the cluster, they sometimes plow through regions of cooler gas, accumulating enough material to reignite star formation in temporary bursts. These events are fleeting. The harsh environment quickly strips the gas away again, but for a brief cosmic moment, the galaxy blazes back to life. What's fascinating is how these reborn galaxies blur the line between life stages. Their stellar populations show stark contrasts, ancient red stars alongside brilliant blue clusters like tree rings recording both droughts and monsoons. Astronomers call them blue ellipticals or rejuvenated galaxies, and they challenge the idea that galactic evolution is a one-way street, yet these second chances are rare. Most dead galaxies stay dead, their gas lost to the void or heated beyond recovery. That makes the exceptions precious cosmic proof that even in the vast, indifferent universe, endings aren't always permanent. Whether through galactic cannibalism, gentle gas accretion, or sheer luck, some galaxies cheat their fates, writing unexpected new chapters in stories we thought had already ended. Every atom in your body, from the calcium in your bones to the iron in your blood, carries a cosmic origin story written in the fires of stars and scattered across the galaxy. The oxygen you breathe, the carbon forming your cells, even the gold in your jewelry, none of these existed when the universe began. They were forged in stellar furnaces and cataclysmic explosions, then flung into space by supernova and galactic winds, eventually finding their way into the cloud that formed our solar system. You are, quite literally, made from the ashes of dead stars and the debris of galactic collisions, a walking testament to the universe's endless cycle of creation and destruction. Consider this: the hydrogen atoms in your body are the only ones that date back to the Big Bang. Every heavier element, like the nitrogen in your DNA or the phosphorus that powers your cells, was crafted in the hearts of massive stars or the unimaginable violence of colliding neutron stars. When those stars died, they didn't vanish quietly. They erupted, seeding their surroundings with these newly minted elements. Galactic winds, those titanic outflows we discussed earlier, then carried this stellar dust across vast distances, mixing it with other gas clouds that would eventually collapse into new stars and planets. Our solar system formed from one such enriched cloud about 4.5 billion years ago, a speck in the Milky Way's spiral arm. The very atoms that now compose your hands, your eyes, your thoughts, once swirled in that primordial nebula. Some might have been part of multiple stars before finding their way here, recycled through generations of stellar life and death. The iron in your blood, for instance, likely originated in a supernova so powerful it outshone an entire galaxy, a final, defiant act that scattered its elements across light years. This connection isn't just poetic, it's measurable. Spectrographs can trace the chemical fingerprints of stars, revealing which ones share compositions similar to our Sun. We've even identified stellar siblings, stars born from the same gas cloud as our Sun, now scattered across the Milky Way by billions of years of orbital motion. Tracking these long-lost relatives helps us piece together our solar system's birthplace, a region that might have looked very different before galactic rotation stretched and twisted it into today's configuration. But the story doesn't end with stardust. Galactic processes shaped Earth's very existence. The Milky Way's spiral arms, where denser gas triggers star formation, might have influenced when and where our Sun was born. Later, the galaxy's gravitational tides could have perturbed comets in the distant Oort cloud, sending some inward to deliver water, and perhaps even the building blocks of life to our young planet. Even Earth's periodic mass extinctions might trace back to galactic events, as the solar system's passage through spiral arms or dense molecular clouds could disturb asteroids or alter cosmic ray exposure. So when you look up at the night sky, you're not just observing distant galaxies, you're seeing your extended family. Those swirling spirals and colliding giants aren't just celestial phenomena. They're the factories and distribution networks that built the raw materials of your existence. The universe didn't just happen around us, it worked for billions of years to create the conditions that allowed atoms to assemble into something that could wonder about its own origins. In the end, galaxies aren't just islands of stars. They're the architects of complexity, the crucibles where simple elements transform into the diversity that makes planets, oceans, and life possible. And that means you, watching this video right now, are one of the most intricate results of galactic evolution, a living bridge between the cosmic and the everyday, carrying the legacy of stars and galaxies in every cell. From the tiniest dwarf galaxies barely holding onto their stars to the colossal superclusters weaving the cosmic web, galaxies defy simple classification. They spin, collide, erupt with newborn stars, fade into red embers, and sometimes even cheat death entirely. The universe crafts them in spiral elegance, smashes them into elliptical giants, and leaves others as irregular splatters across the darkness. Some devour their neighbors while others float in isolation, their stories written in starlight and invisible dark matter. Each galaxy holds secrets. The Milky Way warps like a vinyl record at its edges, Andromeda races toward us in slow motion, and ghostly dark galaxies lurk unseen. Starbursts blaze with reckless creativity, while dead galaxies whisper of past violence. Black holes govern from the shadows, and hypervelocity stars escape entirely, sentenced to eternal exile between galaxies. Even now, as you watch this, galaxies are being born in the distant universe, their light just beginning the long journey toward future telescopes. So here's your invitation. Look up tonight. Even with just your eyes, you might spot the Andromeda Galaxy, a faint smudge of ancient light, our closest galactic neighbor and future collision partner. Or find the Magellanic Clouds, twin dwarfs orbiting the Milky Way, their shapes distorted by galactic tides. Every pinprick of light holds stories of creation and destruction on scales we can barely fathom. Which fact stuck with you? The way galaxies breathe through cosmic winds, how you're literally made from their star stuff, or that most of what holds them together is invisible? The universe doesn't owe us answers, but it offers endless wonders. So keep questioning, keep staring at the stars, and remember, you're not just observing galaxies. You're part of their grand, unfolding story.